I'm certainly not limited to the use of a circuit to do my filtering for me. I can also use software or digital signal processor, DSP, to do that filtering as well on an already sampled signal. If I have a relatively static signal, in this case it's a discrete signal, so I've already sampled it onto something like my Arduino, and I'm plotting versus sample in the magnitude of that. If I have a fairly static signal, it's very easy to see that I can do a pretty good job of removing noise from my signal or filtering that signal by averaging. Right? So that averaging over time would effectively give me a constant filter here that would approximate the real value that I'm trying to get out of this and filter out some of that higher frequency noise. If I have a dynamic signal, in this case it's still discrete, but it's dynamic, there's actual frequency content to the signal, I can't just average over time, right? That'll just give me the mean of my signal, or the DC offset of my signal. What I want to do instead is do a moving average. So that moving average would take a window of samples, calculate the average of that, and then calculate a new window of samples, and a new window of samples, and a new window of samples, right? Obviously, I want to choose the length of that window that I'm going to call L based on the frequency content of my signal. So I don't want to choose too large of an L here, or I'll miss the actual frequencies in my signal. So this is called a moving average filter. And as an example, a 2-point moving average would look like my average here, yi, so I'm at sample I, would be xi plus the previous sample, xi minus 1, divided by 2. And if I wanted more points, I'd take more previous samples, obviously, and divide it by the number of samples that I'm looking at. And this is updating each time. So if I'm looking at the 5th sample, I'm taking the 5th sample plus the 4th sample and averaging those. If I'm looking at the 15th signal, I'm looking at the 15th sample plus the 14th sample and averaging those. So that's what's moving this window along here. As we mentioned earlier, taking more points or using a higher L will lower the corner frequency of my filter. And this is, of course, operating as a low-pass filter as well. It's removing the higher frequency component. It's not a great filter, right? It might approximate something like you might be attenuating things by on the order of 20 dB or so, depending on the number of points that you have in your filter and the like. Some frequencies you can actually eliminate completely based on the length of your filter. But that gets into for more complex math, and the real key points that you want to keep in mind is that more points will lower the corner frequency. It's a low pass behavior. To implement a moving average filter on something like an Arduino, I'm going to use the basic process of keeping all of my data in an array, and I will continually update the data in that array. So my window effectively is defined by my array. In this case, I have an 8-element array, so L is 8. And each time I capture some data from, for example, a sensor pin, I'm going to put it in my array. So maybe I have 23, 30, 25, 15, 13, 12, 17, 19, and then I take my next data point and replace this original element of the array. So say it's going up to 21 now, and then I keep rewriting the data in this array because I'm only interested in the last 8 points for calculating my moving average. So say this is going back down to 21 and so on. Right? So I'm just continually writing data into this array and looping through it. And so the pseudocode that I would use here is I'm going to sum the elements of that array, and there are cleverer ways of doing that, right? I can keep a running sum, just take out the last element before I add the new one, and so then I don't have to loop through this array each time and do that, but I'm going to sum the elements of the array. And in this case, my averaged value will equal that sum divided by 8. And once again, there are cleverer ways of doing this as well. One of the reasons I chose the power of 2 for the number of elements in my array is that I could instead do this division, which, as we know, can result in a float and be fairly complex, right? I can do this division by just bit shifting. So shifting all of my bits to the right by 3 bits, right? That's doing the same thing as divide by 8, but this is a very fast way to do this on a microcontroller, and I still end up with an integer in the end. So it's really simple implementation, which is why something like a moving average filters are a very common thing to actually put to write into your Arduino code if you're trying to measure sensor data. You just have to be very wary about the length of the window or the array that you have that you're keeping data for, and make sure that and the sampling rate is not such that you're losing frequency content that you care about in your signal. Because of course those two things, that L, the size of your moving average, and your sampling rate, are setting that corner frequency. And of course a moving average filter only does this low pass functionality as well. So there are a lot of reasons to do your filters in an actual hardware circuit. There's other reasons to do this in software as well. And obviously there are much more complex versions of filters in software that you could implement. This is the simplest thing and probably the most common thing by far that you'll see.